Okay, so this video is about infinite limits. Actually, in your book, this is under section 12.3. We kind of pair this with chapter 11 because it has to do with sequences and series, but we're going to really talk more about this idea of limits today. It says a vacuum pump removes 25% of the air from a sealed jar with each stroke. The jar starts with 1 liter of air in it. Okay, so after one stroke, 25% of the air will be removed. So that means that we're going to have 0.75 liters of air remaining. And then what are you going to do each time you have one of these strokes? You're going to multiply by 0.75. Okay, so if I multiply 0.75 by 0.75, or if I square it, I will get 0.5625. And if you go ahead and keep track of what you're actually doing, not in the calculator, but just the actual math required, you can easily see the pattern. It's just the power. However many strokes, it is the power. So if I multiply by 0.75 again, I get 0.421875. And if you notice, this is getting smaller and smaller. All right, and so that's going to be 0.75 cubed. And so what would, without having to go through all of the sequences, what would after the 10th stroke be? It would be 0.75 to the 10 power, which you can do easily in your calculator, and you will get 0.056, and these decimals are going to continue to go on a long time. And then for the 100th, you'd think that, oh, this will be really small. Okay, so we'd take 0.75, we'd take it to the 100th power. And obviously in your calculator, it's going to give you this number in scientific notation. We're going to get about 3.2 times 10 to the negative 12th power, or sorry, negative 13th power. So that's a really small number, but it's not quite zero. Okay, what about 500? All right, well, this is going to be 3.39 times 10 to the negative 63. So it's getting really, really small, but it is larger than zero. It is something. Okay, so in general, what we have here is we can actually write this one of two ways. We can, and I'm going to kind of write it over here so we can see it more clearly. Our nth term, the more obvious one, I think, is writing it as 0.75 to the n power. However, we know that this is geometric because you're multiplying by 0.75 each time, so we can use our rule, which says the first term times r, and in this case the first term and r are both the same number. That doesn't always happen, to the n minus 1 power. Now, both of these give you the exact same sequence. Okay? So my next question is, will the amount of air in the jar ever actually reach zero? Now, theoretically, no. There will always be at least a little bit. Even if you could say it doesn't even count, it's still technically there. All right, so as n approaches infinity, remember these arrows we saw in rational unit, these mean approach. So as n gets closer to infinity, or as n approaches infinity, what is the a sub n? What is the amount of air remaining approach? Well, it approaches zero. It doesn't equal zero, but it approaches zero. Okay? So now let's look at the next page, and this is going to be a more general sense of what we're talking about here. We see this LIM here. This means limit, and underneath it you have x approaching infinity. Okay, limits can be where x is approaching infinity, x can approach negative infinity, x can even approach a number in the case of a vertical asymptote or even just a regular point. And so we see here we have 1 over x. This is a rational. This is not exponential or geometric. We're going to kind of bounce around from different functions. So there's not just a rule that we're going to follow depending on the parent function, because we're going to see a lot of different types of functions here, mostly rational though. It says the limit of 1 over x as x approaches infinity means what are the values of 1 over x approaching as x approaches infinity? Basically, for really big values of x, what does this thing equal? Now, what makes sense? 1 divided by a really, really big number is going to be really close to 0. So although we won't say that 1 over x equals 0, the limit of 1 over x is equal to 0. So I want to be clear here. It's not that 1 over a really large number equals 0. It's that the limit of that really small number is 0, particularly as x gets bigger and bigger and bigger. Okay, and that should kind of make sense, and we've been building up to this point. So then on number 2, we have a new problem. Now this is also rational, and if you just plug in infinity here, you'll get infinity over infinity, all right, which is not 1. It's a little bit more complicated than that, okay? So what we're going to do is just a little bit of algebra, all right? And in this problem, it may seem unnecessary, but this is going to be an extremely useful tool. So what I want you to do is just kind of follow along, okay? We're going to take everything on the top and everything on the bottom and divide it by n. Now the reason we're dividing by n is because that is the highest power of x. So I want you to just look at what I'm doing and think about, is this a valid algebra move? Can I divide the numerator by n if I also divide the denominator by n? Yes, it's the exact same problem. Well, now we can see where some things are going to simplify, all right? So if I take, like in particular, and I'm going to switch colors here, particularly as I, and this should have been an n, sorry. As n approaches infinity, 6 over n, we know that will go to 0. And so I'm just going to cross it out because it's like it's not there. What does 3n over n simplify to? 3. What does n over n simplify to? 1. So the answer is 3, and you might have actually made that prediction at the very beginning. Okay. Let's do another problem, and then we're actually going to do all 3 of these, and then we're going to kind of make a conclusion on what you can do in general in these problems. Okay, so the limit as n goes to infinity. Now in this problem, what do you think we're going to divide by? We're going to divide everything by n squared because that is the largest power of n. And I'm breaking everything up so we can just deal with them individually. This is just a clever algebra move to make this problem solvable. Because like in the last problem, if you just plug in infinity for n, you really won't get anywhere. You can't treat infinity quite like a number. There are workarounds, but you can't just plug in infinity in for n. Okay, so again, there's some terms we're going to be able to cross off. In fact, on any of these terms where the denominator has a higher degree than the numerator, we can cross those off. And that should be reminding you of something. What does that remind you of? Hopefully it's reminding you of rationals, and when we compared the numerator and denominator degree, talking about horizontal and slant asymptotes. Okay, so in this case, we don't even have to now plug n in or even visualize it. We've crossed these off, and that took care of that. N squared over n squared is 1. This n squared over n squared is 1, and so we get 1. Now, I want to take just a minute, and let's talk about the similarities of these with rationals. Both 2 and 3 had a numerator and denominator that originally had the same degree. How would you have found the horizontal asymptote? You would have done leading coefficient divided by leading coefficient. And that's what this limit ended up being. Limits in end behavior, very similar. Okay, this is like horizontal asymptote. This is end behavior. All right, it's a different context and a different application, but it's very similar concept. Okay, and the more you think of it cohesively, the better off this is going to be for you. You'll remember it. All right, so you may be thinking, well, these degrees are different, so it's going to work out differently. Okay, so let's go ahead and use the strategy, though, that we did do on the other ones. So what would we divide by? We would divide by the highest exponent, which is n squared. And my air slate does not want to make those tiny squares. And I also need to divide this 3n by n squared. And again, anywhere where a really large value of n will make that term go to 0, we're going to cross those off. And if you notice, I kind of get like a divide by 0 here, which is an issue, all right? But I also get, even if you didn't think of it that way, you can kind of get like a 4n here. No matter what you do, though, you're going to have an issue. So let's just go back and think of this logically. If I plug in a really large value for n, is there any way we could say that the denominator could catch up to the numerator? Like if I have 4n squared, minus 6 doesn't really do anything when you're talking about really large numbers. Okay, the numerator will always be really large compared to the denominator. And as n gets bigger, it's going to get bigger and bigger and bigger. Okay, this we call infinity. All right, and you know, typically we don't say that things equal infinity, but a limit can equal infinity. This is like your slant asymptote. Okay, remember with slant asymptote, you went up maybe steeper, maybe flatter, but this is a slant asymptote. That's why as x approaches infinity, y is approaching infinity, or that we could say the limit is approaching infinity. Okay, let's try some more examples. So this, you kind of hopefully got the hang of this at this point. Some of you are going to pick up on this a lot faster than others, and so I want to encourage anybody who's having a hard time just to use the same strategy we used at the beginning, which is dividing everything by the highest exponent of n. So I'm going to divide 1 by n, I'm going to divide 2n by n, and I'm going to divide 5n by n. And any term like 1 over n, that's going to go to 0 for really large values of n. And what you're left with is a negative 2 over a 5, and that is your answer. Okay, 6 is a little bit different. Again, though, let's just use the same strategy and then decide what's happening. So here you would actually be dividing by n cubed. It's always going to be the largest exponent of n. If you don't do the largest, you're just going to get stuck and not be able to figure out what your answer is. Okay, so in this problem, both things in the numerator cancel out. Okay, so this limit of the numerator is 0, and of the denominator is 1, 0 over 1 being 0. And this should be, you know, you should remember this with rationals. This is the parent function case. This is where the horizontal asymptote was y equals 0. So it's just like horizontal and slant asymptotes, really, when you're taking x going to infinity. Now I'm going to switch it up later, and we're going to do other limits. But for these, it's not bad. All right, let's look at 7. 7's kind of strange. 7 has this negative 1 to the n. All right. Other than that, though, what would be the limit? Let's say this had not been there. See how, if you're picking up on this at all. The limit would have been 1/2, okay? And you just use the same strategy, okay? So I'm going to put a little dot, dot, dot. The limit would have been 1/2 without this. But with this, what's happening is, even for large values of n, you're doing even, odd, okay? So sometimes it's positive 1/2, sometimes it's negative 1/2. Now, you can't have a limit that's two different numbers, okay? And so when you get something like this, you're just going to write DNE, does not exist. I don't want you to write no solution or the no solution symbol, because this is not, you're not solving for x here. All right, so but you can abbreviate with DNE, does not exist. All right, so what do you think about the next one? Is this one a does not exist because of this? Well, let's see. All right, what would have been the limit without that? The limit would actually, in this case, be 0, because it's like number 6, where the denominator has the larger degree. You can definitely go through and use that same strategy, though, that I used on the others, okay? But let me ask you this. Plus minus 0, is that two different numbers, or is that one number? It's one number. It's 0. So I don't want you just to look at the negative 1 to the n and immediately go DNE, does not exist, because it could exist, and this is an example of when it does. Okay, let's look at the next one. Again, we have this negative 1 to the n. If the limit would be 0, the negative 1 to the n won't matter, but if the limit is going to be another number, it's a does not exist. So what do you think? Okay, it's a DNE. Hopefully that's what you were saying with enthusiasm out loud wherever you are watching this video. Okay, it does not exist because the limit would have been 5/2. All right, let's look at the next one. Again, it could be DNE, it could be 0. We're not really sure. What do you think? And it may help you just to consider that there's like a 1 there. Okay, way. Without the negative 1 to the n, the limit would be 0, so the negative 1 to the n, although it is causing an oscillating of positive, negative, in the end, the limit approaches 0. Okay. Number 4 looks a lot weirder than it really is. So let's think about what the degree truly is of the numerator. Okay, that's easy. 1. What is the degree, though, of the denominator? Truly. Okay, truly the degree is also 1 because you're square rooting a square root. So it's weird, okay, but we got to get over that. Math is going to be weird from now on. So if the degrees are the same, all right, going back to what we did, this is why we want to be able to think of it like asymptotes, because the dividing by n here would be kind of tricky. What do we want to do? Or what do you think it is? I really want you to be engaged and not just writing this down. The more you're thinking about this critically, the more you're going to really understand what's going on here. Okay, so when the degrees are the same, you use the leading coefficient, which would be 4. If you did this by dividing by n, by the way, it's a little weird because what you would have to do is you would have to divide 4n by n, but in this square root, you would have to divide by n squared because it's underneath the square root. But you can do it this way. You can actually do any problem this way. The numerator would simplify to 4, the denominator would simplify to 1, so you get the same answer either way. Okay, so let's use, though, the simpler strategy on this next one. Is this one where the degrees are the same? Yes, for the exact same reason. All right, but I do want you to notice that there's a negative right there. So we're just throwing this in on the last one, and we'll talk about this. Okay, so it's going to be 2 over root 3, okay, but we need to put a negative on there. And you don't have to simplify it. This is a good enough answer. Okay, bring your questions to class.